Hello, I'd like to start by thanking you all. I am Mustafa Tan and I have been with the Prota team for almost 20 years. I'm acting as the product manager and software architect for ProtaStructure. Today, I will be talking on the seismic design capabilities, OpenSeas integration, and performance-based design features in ProtaStructure. Of course, as you appreciate, it's not possible to fully demonstrate the topic in a limited time. The purpose here is to give you an overview. Time is of the essence, so without further ado, let's begin. ProtaStructure supports a wide range of international seismic codes. The scope includes base shear calculation, irregularity and building checks, seismic design and detailing. Eurocode 8 and national annexes, Romania, Turkey, IBC, UBC, Philippines, Indonesia, India, Thailand, and Peru seismic codes are supported currently. As of this date, Colombia seismic codes are under development. ProtaStructure provides a comprehensive wizard for parametric calculation of elastic and design spectra according to chosen seismic codes. For weak soil conditions or special one-off projects, you can also introduce user-defined site-specific spectra. An important seismic code that we support with ProtaStructure is the Peru seismic codes. You can select the region, province, and district, and all necessary parameters and acceleration spectra are automatically calculated. All seismic checks, including irregularities, drift checks, and ductility requirements are automatically conducted. Colombia seismic codes are currently work in progress. With ProtaStructure 2022, you can now calculate seismic loads according to Romania P100 and Eurocode 8 provisions. You can select the county and city, and all necessary parameters and acceleration spectra are automatically calculated. All seismic checks, including irregularities, drift checks, and ductility requirements are automatically conducted. Indian seismic code is also among the new seismic codes we have supported in 2022. Similar to all other codes, you can use the parametric wizard to choose your project's code-based parameters and calculate the acceleration spectra for base shear calculation and more. ProtaStructure will allow you to use different design spectra for the two different orthogonal directions, except for Eurocode 8 at the moment. That means you can use different structural systems in each direction for a more economical design. Site coefficients FA and FV on seismic parameters window are now user-editable for US, Indonesian, and Thailand codes. This will help you to adapt to different regional implementations of US codes. These parameters will revert to their code-based values when site class is changed. As a comprehensive solution for seismic design, ProtaStructure automatically compares the response spectrum base shear to the equivalent static base shear and scales up the internal forces and displacements. This scaling is not done up to 100% of equivalent static base shear, depending on the selected seismic code. Besides, scale factor changes with the existence of any structural irregularities in the system. Usually, if the structure is irregular, there will be a penalty in base shear scaling by utilizing a larger factor. RSA scaling factors for regular and irregular cases are now user-editable in ProtaStructure. Diaphragm assumption is one of the major considerations in building type structures. ProtaStructure has comprehensive options for diaphragm modeling. ProtaStructure will automatically detect the existence of one or more rigid diaphragms on a floor level by checking the touching or stepping slab boundary conditions. You can even exclude some of the slabs from the diaphragm formation. As a result, A floor level can consist of a single rigid diaphragm, multiple independent rigid diaphragms, free nodes, or combination of both. Regardless of the slab conditions, you can force the entire floor to act as a single rigid diaphragm or no diaphragm at all. If you want to consider the in-plane flexibility of the slabs and other members, you can do so with the flexible diaphragm option. In this case, the floor must be meshed and rigid diaphragm assumption must be turned off for the particular story. You can even adjust the in-plane stiffness properties of the slabs. It may be costly to mesh all stories in a building, especially when it is not really necessary. ProtaStructure will allow you to mesh only the preferred stories, such as basement floors, transfer floors, podium to tower transition floors, etc. Shear wall modeling is a crucial part of structural analysis and design process. That's why we offer different options for shear walls. Rectangular walls can either be modeled with mid-pier or finite element shell elements. While mid-pier option provides an economical and fast way to model regular continuous rectangular walls, they are limited when it comes to irregular discontinuous walls or core walls. Short walls, whose behavior is dominated by shear, must also be modeled with shell elements. Rectangular wall panels can be merged into complex core walls. Analysis, design, and detailing are done considering the combined section. Core walls are always modeled with shell members, regardless of the default wall modeling option, especially because of potential torsional behavior depending on the structural configuration. It is also possible to display internal force diagrams of rectangular or core walls modeled with shells. Group sums are automatically calculated for the core walls, and a single diagram is displayed. Core walls are assigned separate pier definitions similar to rectangular walls. Groups and section cut definitions for rectangular walls and core walls are now automatically communicated to other structural analysis software for your convenience. Existence of coupled shear walls affects the ductility of the structural system, and the proper modeling of coupled walls are also important. The coupling beams connecting two shear walls tend to suffer from shear failure. That's why their shear design and detailing are different. Besides, seismic codes may require different cracked section properties for these coupling beams. That's why ProtaStructure can treat them differently in analysis. Also, post-analysis checks are conducted to assess the effectiveness of a coupled shear wall. Seismic codes may require the use of cracked section properties for different member groups and different degrees of freedom. ProtaStructure provides an extensive table for specifying the section modifiers with default values complying with the selected seismic code. You can even use these stiffness modifiers only in some of the load cases. That means you can use uncracked sections for a gravity combination and cracked sections for a lateral combination. ProtaStructure will internally use two stiffness matrices for calculating the results. Depending on the design code and seismic code you have selected, ProtaStructure saves you time and automatically generates the load cases and combinations. You just need to specify the gravity and lateral loading options. Combination factors are determined based on the selected code of practice. You can then customize the load cases and combinations further. Maybe the most important step for a seismic analysis is the calculation of the masses in the structure. ProtaStructure derives the masses from various sources such as self-weight, imposed loads, user-defined loads, slab loads, infill wall loads, snow loads, and user-defined vertical load cases. In addition to this, each story can have different occupancy and live load participation factors. At the heart of the seismic analysis is the determination of undamped free vibration modes of the structure. These modes are used in equivalent static or response spectrum analysis. ProtaStructure automatically calculates the vibration modes by a 3D subspace iteration eigenvalue analysis. Dominant modes are detected and sorted with respect to their mass participations. Cumulative mass participation is also checked in response spectrum analysis. Masses can be lumped or distributed with rotational inertia, and 3D torsional modes and local modes can easily be detected. The calculated period of vibration is automatically compared with the upper limits in seismic codes, which are calculated by empirical formulas or Rayleigh equation. The simplest method of base shear estimation is done by the well-known equivalent static load method. This method makes use of the dominant mode of vibration at each direction. ProtaStructure automatically calculates the base shear and distributes it to story levels by using the seismic mass and the story heights. If there are multiple diaphragms or free nodes, the load is shared among them. Accidental eccentricity is automatically calculated, and irregularity penalties are automatically applied. Since equivalent static load method is an approximate method and based on dominant mode behavior, it is not applicable to all buildings, especially if the building has vertical or horizontal irregularities which lead to higher mode effects. Also, if the building height is beyond specific limits or spectral accelerations are high, again the equivalent static load method may be limited by the seismic codes. The table here is only an example from US codes. ProtaStructure conducts the applicability checks for the analysis methods for selected code of practice and warns the user if EQS analysis is not appropriate for the building. Unlike equivalent static load method, the response spectrum analysis can take the higher mode effects into consideration. The model responses are combined with CQC methods. ProtaStructure can incorporate additional eccentricity in model analysis by introducing the eccentricity load vectors during the analysis. Code checks such as RSA to EQS amplification and cumulative mass participation checks are automatically done. As you know, response spectrum analysis calculates and combines the pseudo-maximum responses of natural vibration modes against a given design spectrum by assuming each mode as an independent single degree of freedom system. During the combination of model result vectors, the sign of the displacements and internal forces are lost, and hence equilibrium condition is not satisfied anymore. If you check the deflected shape of the structure under response spectrum load cases, you may see weird displaced shape due to this fact. Also, internal force diagrams will always be positive after the combination. This is the expected behavior, natural output of response spectrum analysis. Most of the time, this is easily overcome during the design by combining RSA load cases with dead and live load cases using both negative and positive coefficients. However, for deflection checks and other structural checks, you may need the signs of the internal forces and deflections. For this purpose, ProtaStructure hosts a setting to either use the absolute values or sign of dominant mode for RSA result signage. If dominant mode signs are used for overall RSA results, then the dominant mode will be selected depending on its mass participation in a certain degree of freedom, and the sign of that mode will be used for the particular RSA load case in the relevant direction. This approach may yield unexpected results in highly irregular structures where the dominant mode is a torsional mode or translational mode with high coupling. Vertical earthquake component can be prominent, especially if building has large spans, transfer beams, transfer floors, long cantilevers, discontinuous columns, etc. The vertical component can cause unexpected axial strains and vibrations. Seismic codes usually calculate the vertical components as a percentage of horizontal component and amplifies the gravity load case results. ProtaStructure follows this simplified methodology as explained in the codes. For some cases, codes require a vertical model analysis to take the vertical component into consideration by the help of a vertical acceleration spectrum. This methodology requires a careful identification of vertical masses and detection of necessary vertical local modes. Seismic design of buildings with basements require special attention. Since they are usually underground, the earthquake forces calculated for the basement stories must be handled differently and integrated into the superstructure. Besides, basements are usually excluded from irregularity checks. On top of this, some of the seismic codes require using a different stiffness modifier for basement walls. Because of their aspect ratio, basement walls must always be modeled with finite element shell elements. That's why we support a dedicated basement wall type in ProtaStructure. Since the stiffness properties of the basement stories are different than the superstructure, the seismic codes require a two-stage analysis of such structures where basements and superstructure analyzed separately and results are combined. ProtaStructure can utilize different mass and stiffness matrices to perform a two-stage analysis. In the first analysis, basement masses and seismic loads are eliminated. Only the mass of the superstructure is used. Stiffness of the basement story is still present. In the second analysis, mass of upper part of the building is ignored and loads in basement story is calculated. Stiffness of the upper structure is not ignored. Then results are combined. I want to open a parenthesis here for the loading on the basement walls. An essential type of loading is the static and dynamic load of soils on basement walls and parts of the building that act as a soil retaining structure. ProtaStructure allows you to specify your soil profile, water table, and surcharge loads. Then, static and dynamic soil loads will be automatically calculated and assigned to shear walls and basement walls. You can do further editing on the calculated loads and even create a detailed report. Let's stray away from the buildings for a brief moment. ProtaStructure is capable of designing and detailing components independent of buildings thanks to the engineering library in Prota details. Every now and then we need to design retaining walls. ProtaStructure has a very powerful retaining wall module which is capable of calculating dynamic forces and perform the design accordingly. Especially for the buildings with basements, the determination of the building height is a vital step. In ProtaStructure, the user specifies the number of rigid basements. In other words, user decides the building height and building base. However, the basement stories need to satisfy certain conditions in order to qualify as basement. One method is to compare the superstructure period to the entire structural period. Of course, the rigid basements should also physically satisfy the required conditions. That means they should have surrounding basement walls and have a significant stiffness difference than the upper structure. After the verification of building height and building base, ProtaStructure will calculate seismic loads considering the basements and exclude the basement stories from irregularity checks. Building effective top story is as important as the basement stories. Mostly, the top stories include elevator maintenance shaft or similar mechanical facilities. The supporting structure at the top story usually has lower stiffness and lower masses. Performing irregularity checks including the maintenance story may be unrealistic depending on the project. Also, most of the seismic codes require the calculation of an additional concentrated point load at the top of the buildings in EQS method. Applying such a point load at the maintenance structures may yield unrealistically large sections. So, ProtaStructure provides a tool for engineers to use their engineering judgment and set the effective top story of the building. Effective top story stiffness and mass are still considered in the analysis, but they are excluded from irregularity checks, and the additional concentrated top story load is not applied. ProtaStructure will check horizontal irregularities and apply the penalties automatically for equivalent static load methods. If floor torsion irregularity exists in the structure, ProtaStructure will increase the additional eccentricity and repeat the analysis with the new eccentricity value. In case of excessive floor torsion, equivalent static method will not be applicable and ProtaStructure will warn the user. Diaphragm discontinuity must be detected by the engineer. However, ProtaStructure provides the necessary tools to handle the cases where rigid diaphragm assumption is not valid. ProtaStructure will check the slab discontinuities and exclusions and decide on the multiple rigid diaphragms and free nodes on a floor level. Besides, flexible diaphragms can also be used where rigid diaphragm assumption will not be valid and in-plane stresses need to be evaluated. For buildings having structural frames non-parallel to the specified earthquake direction, the 30% rule can also be applied in the combination wizard. When activated, 30% of the other direction earthquake results will be added to the primary direction combinations. ProtaStructure will also check the vertical irregularities and present a detailed report. Soft story, extreme soft story, irregular vertical distribution of mass, weak story and extreme weak story are among the vertical irregularities that can be checked automatically after the analysis. As I specified before, basement stories and effective top stories are excluded from irregularity checks. Relative drift checks are always a major part of seismic checks and a strong indicator of damage vulnerability. ProtaStructure performs the relative drift check for each story and presents in a tabular format. The critical member exhibiting the maximum displacement is indicated in the report so that you can review it in your model. The drift check in ProtaStructure can also recognize and identify the intermediate nodes of a column inserted as a single piece from top to bottom. The second-order effects requirement is another important post-analysis check. It evaluates the moment created by weight of the structure under lateral displacement to moment created by the story shears. If the ratio is too high, then the structure may be susceptible to second-order effects and a detailed review must be done. As the name implies, this is a stability check under seismic loads that compare the overturning moments to resisting moments. ProtaStructure can perform strong column checks of reinforced concretes and steel special moment resisting frames according to ACI, Eurocode, and Turkish earthquake codes. In addition to new code coverage, the strong column weak beam and joint shear check reports are written from scratch to include more visual components with intelligent notifications. Strong column, weak beam, and joint shear checks can now be reviewed for a single column and beam while designing their reinforcement. In this way, you can fine-tune the design while keeping an eye on the global seismic checks. The status of these checks can also be reviewed using the new visual interrogation options. For the beams spanning into the columns from different axes or elevations, you can treat them continuous or not in joint shear checks. Vertical and planned continuity tolerances can be utilized to achieve this. For flat slab buildings or for buildings where we have floor plan irregularities like diaphragm malformation, large openings, discontinuities, we must check the safe transfer of lateral inertial loads from slabs to walls. This check calculates the unbalanced shear force between top and bottom shear wall and checks if this is resisted by shear friction on the shear wall slab overlapping surface. If not, additional dowels are calculated. For excessive situations, additional longitudinal bars are calculated in connecting beams. The calculated additional bars must be manually provided by the user. For the cases where rigid diaphragm assumption is under question or not valid, we must check if the lateral inertia forces are transferred safely by the floor. For this purpose, the in-plane tensile, compressive, and shear stresses should not be exceeded. ProtaStructure 2022 can calculate forces acting on non-structural members and their connections to the building. Just specify the non-structural members and their properties, and ProtaStructure will automatically calculate the story accelerations and forces depending on the analysis type. To avoid pounding damage in adjacent buildings, we must provide spacing between structures. If you need to design the seismic separation between two buildings, you can use the seismic joint design tool in ProtaStructure. With this tool, you can either load the displacements of an existing ProtaStructure model or enter the second model's displacement values manually. To assess shear force or bending moment sharing in frame-wall interaction or dual systems, you may want to review the moments or shear forces carried by different wall groups to the overall overturning moment or base shear. The wall grouping functionality in ProtaStructure allows you to create groups of walls and assess the base shear and moments carried by them against the structural output. ProtaStructure will design the beam reinforcement under the envelope actions of all combinations, including the seismic loads. For the ductile design and detailing of beams, minimum reinforcement ratios and constructive rules of seismic cause are applied, confinement zone lengths are automatically determined, and links are designed in span and support regions using capacity shear forces. Secondary beam, primary beam connections in reinforced concrete structures require special attention. Usually, hanger links are required in the vicinity of the secondary connection. Hanger links are also required in the primary beam where a transfer column sits. This is prominent especially for vertical earthquake effects. ProtaStructure will now detect such situations and provide hanger links automatically. Similar to beams, ProtaStructure will design the column and shear wall reinforcement for all combinations, including the seismic loads. For the ductile design and detailing of columns and shear walls, minimum reinforcement ratios and constructive rules are applied, confinement zone lengths are automatically determined, and links are designed in span and support using capacity shear forces. End zones are automatically calculated by a percentage of length. Seismic moment envelopes are used in shear wall design. And for columns, links inside the column section are automatically laid out considering the confinement requirements. For example, user can choose to use a single link only. In this case, the insufficient confinement will be satisfied by automatic introduction of cross ties. If the user prefers a double link layout, then the confinement will be satisfied with double links if applicable. Otherwise, cross ties will be used in addition to double links. For an effective column detailing, ProtaStructure offers comprehensive options to cover a wide range of constructability and code scenarios, such as optional lap splices in column mid-height, bob anchorage options such as anchoring into the beam or U-bobs, lap splices and extensions in sloping and narrowing columns, and providing links in joints. ProtaStructure supports different shear wall horizontal web bar layout options for ductile detailing. The conventional practice is to wrap the horizontal web bar outside the end zone longitudinal bars, which is the first option. Second and third options provide better confinement by putting web bars completely in the core or crank them into the end zones. These kinds of detailing options are suggested by some of the seismic codes. For the walls with openings, peripheral bundle bars are automatically detailed around the opening. Designing end zones or boundary elements in shear walls is a challenging task, and different codes suggest different approaches. In ProtaStructure, you can automatically lay out end zones by using a percentage of related wall lag. End zones of the core walls with known shapes such as E, C, L, T, or H can be laid out automatically using the polyline column editor. The percentage of end zones concerning the wall lag can be specified by the user. For random shapes, full automation is not always possible, but we have developed tools to make it as easy as possible for you to insert the end zone rebars. ProtaStructure offers a practical and seamless workflow for assessment of existing buildings and performance-based design. If you have the detailed blueprints of the building, you can enter estimated or exact reinforcements in the members. Corrosion and rebar realization factors can be entered for all members if there are differences between the survey and blueprints or the bars are corroded. A global coefficient for building information level can be entered to factor down member capacities. This factor usually varies between 0.75 to 1, depending on how detailed a survey is done on the building. You can assess the structure simultaneously for different performance targets under different earthquake levels. The assessment and retrofit workflow is the same for all seismic codes in general. In addition to this, plasticity definitions, time history, and pushover analysis procedures are usually generic. However, member-by-member assessment procedure and performance limits may vary in different seismic codes. 4 different analysis and assessment techniques are present in ProtaStructure. Displacement-based linear elastic method deals with relatively regular structures with high model mass participation. In this analysis, yield curvature of the members are obtained with a nonlinear fiber section analysis. Then, a linear elastic analysis is conducted under elastic spectrum with no eccentricity and importance factor introduced. Plastic rotations are estimated from linear chord rotations and yield curvatures. There are also additional checks ensuring ductile failure of the members. Member plastic rotations are compared with the code-specified limits. Risk assessment is a relatively faster method to decide the risk status of an existing building. It focuses on the critical story of a structure, and target performance level is somewhere between life safety and collapse prevention. Single-mode static pushover and nonlinear time history analysis are well-known analysis techniques in the industry, which are quite generic in conduct. However, material nonlinearity definitions may vary in different seismic codes. One of the strengths of ProtaStructure resides in the ability to conduct nonlinear pushover and time history analysis for assessment and performance-based design of buildings. We achieve this by OpenSys integration. OpenSys is an open-source software framework for simulating the seismic response of structural and geotechnical systems. OpenSys has advanced capabilities for modeling and analyzing the nonlinear response using a wide range of material models, elements, and solution algorithms. Nonlinear analysis requires a wide range of algorithms and solution methods. OpenSys provides nonlinear static and dynamic methods, equation solvers, and methods for handling constraints. ProtaStructure analytical model is communicated to OpenSys via TCL files. In addition to the detailed analytical model, nonlinear material properties are also automatically calculated and added on top of this model. The entire structure is then ready for performance analysis. For a successful OpenSys integration, a considerable amount of pre-processing and post-processing is necessary. All the material nonlinearities have to be generated and sent to OpenSys. Column, beam, and wall sections can be modeled with fiber elements and analyzed with state-of-the-art numerical techniques to derive the moment curvature relationships. Confined and unconfined concrete regions can be specified. Strain hardening is taken into consideration. For a more accurate analysis, you can even create the fiber mesh around rebars. For column and wall members, a finite-length hinge zone model with 6 integration points is used. Shear wall members are modeled with distributed plasticity model, again with 6 integration points. Force deformation relationships for integration points are obtained from fiber section analysis. Single-mode static pushover analysis is performed using ProtaStructure OpenSys integration with the plasticity models that I have just described. Parameters such as the number of steps and target displacements can be controlled by the user. After the analysis, the capacity curve is obtained, and users can specify the monitored node for which the curve will be generated. Results can be examined at any desired step. A detailed performance assessment report is generated after. A vital step after the pushover analysis is to find the demand that a target code spectrum requires from our building. It is also known as the performance point. A target displacement identifies the performance point. After plotting the capacity curve, ProtaStructure can detect the target displacement according to FIMA, Eurocode 8, or Turkish codes. The nonlinear time history analysis can be performed using ProtaStructure OpenSys integration. A set of multiple ground motions can be applied simultaneously in X and Y directions. As specified by the earthquake codes, the ground motion application direction is rotated by 90 degrees and analyses are repeated. The selection of suitable ground motions is up to the user. Parameters like fault mechanism, soil properties, magnitudes are of importance. The selected ground motion records are automatically scaled by ProtaStructure using the simple scaling method. After the time history analysis, the results from multiple ground motion sets are automatically post-processed. The average values of absolute maximum responses are extracted and used in performance assessment. A detailed performance assessment report is presented. Additionally, the analysis results for a specific ground motion at a specific time step can be looked up by the user. To visualize assessment results, ProtaStructure can present the member damage regions and risk status by new color-coded visual interrogation options. One of the mostly utilized retrofitting strategy is to use reinforced concrete walls inside the existing frames. This method improves the overall lateral behavior of the existing building, especially by limiting the lateral deformations. In ProtaStructure, you can insert retrofit walls in your existing structures. Modeling of the existing structure is no different than the new buildings. Before the assessment, you must provide preliminary longitudinal and horizontal bars in the retrofit walls. After the assessment, you can design the top and bottom dowels that connect the retrofit wall to the existing frame. Detailed drawings and quantity takeoff can be done in Prota details. Reinforced concrete column jackets can be used to locally improve the axial load and moment capacity of an existing column. Depending on the extension of the longitudinal bars into the upper story, the reinforced concrete jacket can resist moments or not. This can be set as an option in ProtaStructure. If the jacket is set as non-moment transferring, ProtaStructure will assign the moment releases to both ends of the jacket, which will make it only to resist axial loads and shear. If the existing column is too damaged or weak, you can also delete the existing column in order to eliminate it from the analysis and assessment. When a column jacket is introduced, ProtaStructure inserts a second column at the same location of the existing column. The reinforced concrete jacket has the new material grades and it has a hollow section geometry. The jacket can be reinforced similar to the normal columns. ProtaStructure is also capable of retrofitting and assessing beam and column members confined with carbon fibers. The CFRP confinement has a positive effect on shear resistance and axial load capacity of members. Base isolators can be used as a retrofit technique as well as a brand new design strategy against seismic excitations. Base isolators simply concentrate the lateral deformation at a relatively soft isolation layer. They also elongate the vibration period of the building so that less spectral accelerations are experienced. However, soil conditions must be carefully investigated for a possible resonance situation. Besides, the isolators introduce additional damping to the superstructure accelerations, and they help reduce the relative drifts in the upper structure, allowing an almost rigid body oscillation. In ProtaStructure, you can insert seismic isolators anywhere on the columns, since the base isolation is not necessarily at the foundation level. You must have decided on the isolator units, layouts, and lateral and axial capacities before modeling them in ProtaStructure. Please note that you can only perform a linear elastic analysis with base isolators in ProtaStructure. That means they can be used to design and verify the superstructure. This section view is from a seismically isolated hospital. As you have noticed, the columns are isolated at the basement ceiling, where the elevator shafts are isolated at the foundation. This example is a new hospital design. Here you see the base isolated model on the right, and the conventional fixed foundation option is on the left. The base isolated model clearly exhibits a rigid body deformation at the superstructure level. Well, this ends my presentation today. Thank you so much for reserving this session to me and for your participation.